So I'm Dr. Ben Diggles. Some here might know me from I've 30 years as a marine biology editor in Fishing World magazine, but I'm also a aquatic animal health specialist. And why are we here? And unfortunately, it's a sorry state of affairs, but this is not an unfamiliar picture that we're seeing here. And fish populations in New South Wales are under significant threat from declining water quality. I'll start just with that statement. There we go. So clean water is the life-sustaining ingredient that underpins the survival of these fish species. And it's not only about the fish, it's about the whole ecosystem. If they haven't got anything to eat, you won't have any fish. And that's those sort of details. You'll hear a lot about that tonight from our expert speakers, Matt and Kirsten. So healthy aquatic ecosystems, and it's actually non-negotiable. Without water quality, you do not have healthy fisheries. And so this actual project, the idea for this project arose from recreational fishers who contacted me, worried about water quality, and we were trying to work out exactly what can we do about it. And from that arose this concept of developing a community-driven water quality audit or assessment process. And the idea to get actual water quality data, make it available, make it publicly available, to, I guess, broach this topic in a way where we can potentially identify trouble spots and help drive restoration projects with the aim to fix underlying causes of water quality decline to improve fish stocks and fisheries. There's various aspects. Obviously, it's a very large subject to broach. But one thing we wanted to point out here is we're not talking about the quantities of water. So obviously, without water, you don't have fish. But in New South Wales, if on issues related to water regulation, environmental flows and things like that, there is legislation involved in many parts of the state about that. We're actually not here to talk about the quantities of water, even though obviously that affects water quality as well. What we're here to talk about is quality of waters. When you have water, but it's not good enough or suitable for aquatic life, or it's compromised in a way that we think we can improve it to the betterment of our aquatic ecosystems. And no doubt most of you or all of you be aware of these large fish kills that occurred, say, around Menindee Lakes a few years ago. And that was a really sad situation, but it really brought this problem to a head in this state, I think. That was the final straw for many people. And indeed, that's when the recreational fishers who I knew were contacting me about it. And some in the room here are actively involved with some of the work there. But water quality is not only a lethal, can be a lethal issue for fish. There's a lot of sub-lethal effects, and indeed most of the issues relating to how water quality affects our fish stocks are sub-lethal. And they're not, I guess you don't see large numbers of dead fish. It's very unusual in that respect. Most of the problems occur out of sight, out of mind, either in the plankton or other things that you don't see, but the outcome is no fish. And one of those issues when we see the fish can give us some signs, as when the water quality declines, they become more susceptible to disease. This is a golden perch it's an EUS disease. It's actually caused by a fungus that occurs in freshwater systems, and it's sort of an indicator of water quality issues. But when we talk about the quality of the available water in this state, and indeed in this part of the state, it's a sad situation. So Richmond River, 87 fish kill events since 1970. And I know Matt here probably has more to say on this. This is his local river. But these are devastating photographs for fishermen in particular. So yes, there's issues. And another aspect of this problem, I think, is what we call shifting baselines. And that's a term that was developed by actually a fisheries scientist, Daniel Pauly, and not so long ago, 1995. And that describes the slow degradation of these ecosystems over several human generations. So it's very rare that this happens overnight. And the issue is with shifting baselines, each new generation considers a slightly degraded system as normal. And then over several generations of people, this leads to acceptance of degraded fisheries or a degraded environment as normal. And the other way of saying that is death of 1,000 cuts. And that's a real, it's a real issue with basically humans having a relatively short lifespan. And an example for me that really brought this home was I was developing restoration of a 1 hectare shellfish reef. I come from Bribie Island in Queensland, so it's just north of Brisbane. We restored a 1 hectare shellfish reef near where I live and did baseline before and after. And we increased the number of fish by 16 times just by replacing a reef that used to be there. Used to be thousands of hectares of these reefs in that part of Moreton Bay. And so where are all the fish gone? To me, this suggests that what we thought, well, what most people consider a healthy part of Moreton Bay, it's in a marine park, it's a commercial, fishing is excluded from the area, it's a recreational only area, yet we put a reef back in, just a small patch of reef compared to what it used to be, and we have 16 times more fish. We're down to less than 10% of what was originally there, and probably 5. So that's 20 times less fish than what there were 100 years ago. That's a shifting baseline. So water quality is also prone to this shifting baseline. I think what past generations would consider polluted river to us is normal. And it's been really great, and we must thank Ozfish Unlimited for helping us getting the message out about the importance of this. And obviously Ozfish are, I think, Australia's premier fish habitat restoration group. But there's no amount of habitat restoration will work in a fisheries if your water quality is not adequate. And a good example again in the US, where they do similar shellfish restoration in Chesapeake Bay than we've tried in Pumice Passage. Sometimes they have massive problems with dead zones, no oxygen in the water at certain times a year. So in the US, they're not getting as good a results as we get in Moreton Bay for the same, say, hectare of shellfish reefs, because half the time they'll have a dead zone of no oxygen flowing through the restoration zone and killing all the oysters and the other animals. So the trick's obviously not to let things get as bad as that. So that's, I guess, the catalyst of this project. It's funded by the New South Wales Recreational Fisheries Trust. And the title, Community Water Quality Audits. It's a journey towards breathing life back in New South Wales waterways. These things have taken decades to get to where we are now. You can't fix them overnight. So this is part of I guess, the start of a journey, and this is stage 1, and it's a scoping process. That's what we're doing here now. So we're developing this concept of community-driven water quality assessments, audits, to make this water quality, gather the water quality information, make it publicly available, and use it to make decisions. We also, as part of the process, looked at literature review and tried to see what else has been happening around the world and within Australia. There's some good concepts that have been occurred, such as CSIRO has something called Eye on the Water, which we're looking at quite closely. Might be able to integrate with that. Overseas, there's things like Know Your Water Quality Index Calculator from the USA, which seems quite similar in many respects to what we had envisaged here. So we're gathering ideas from around Australia and around the world on how this might work. And we want to work closely with fishers and other members of the community to determine what the water quality assessment process would look like. and obviously how much of that would be likely to cost, because that's stage 2 and 3 of the projects, actually to go out and do some trials. So we're meeting with rec fishers throughout the state. And we're looking also at the end, there'll be opportunities to identify areas in the local region here where you think we might be able to do some of these water quality monitoring or indeed restoration programs. This is the first meeting, so welcome all, and it's great to see you here. So, as I said, for the future phases of this project, we are looking for suitable locations to undertake the monitoring and restoration in a pilot implementation stage. And all going well, leveraging off that, if we're getting good results, looking at maybe developing a model where we could roll this out more broadly across the state. That's all in the future. We do have a survey that we want you guys to, we encourage you to fill out. You'll have an opportunity at the end. That's the link to it through the QR code, but don't worry about that. You'll get to see that a bit later. And our team, as I said, I've already introduced myself. I think we've got a team of very experienced and diverse experts in the field of water quality, fish health and fish biology. And obviously, as I mentioned before, AusFish are helping out the Foremost Fish Habitat Group. So it's myself there in the top left, Professor Kirsten Benkendorff down here, Benkendorff, Southern Cross. Craig Copeland, who's not here tonight, he set up AusFish probably over 10 years ago now. Dr. Matt Landos talking tonight, up next. He's a very experienced, I think, Australia's best fish vet, bar none. If you've got sick fish on a farm and you've got multiple millions of dollars of animals in the water, this is the guy I'd be telling you to ring up to fix them. Matt Hansen is the recreational fisher who bugged me with this idea, and between us we devised this concept. And Dr. Stuart Rowlands, also known as the Codfather. Unfortunately, Stuart's can't be sort of with us tonight due to health reasons, but he's been helpful in the extreme in providing us with some background and some perspective on this in relation to the freshwater fisheries. So that's our team. The agenda tonight, so we started a little bit late waiting for people to come in, but I'll be finished very shortly. Matt's up next, joining the drops, Water Makes Fish. Then Kirsten, who actually has probably the majority of publicly available water quality data in New South Wales, or stuff that we can rely on, or at least you can get your hands on. And then we're going to open it to the floor to discuss any local water quality issues or trouble spots that you know of locally. And then we'll round up where to from here and close the meeting. So that's the agenda. Again, thank you all for coming. Over to our other presenters. Next one up is Matt Landos. It must have just gone to sleep.
All right. So first I want to sort of tell a bedtime story, I suppose. We're quite a small group here. How many scientists are amongst us? Science backgrounds? None. Right, we're starting in the wrong couple. Okay. So for a couple, we're probably going too far, and everyone else, hopefully we're going to land on the spot. Now, how do we make fish? Well, first we need some key ingredients. So we need them to be fertile and reproductively functional. Right, that's the bedrock. Got to have bits working. Then we've got to have them sending the right signals. Now, what's amazing really to me is that fish are almost exactly the same as us. They're just in water. So my training is as a veterinarian. And so on day one, I learned about a dog. And then by week 2, I'm learning about a horse. It's a dog. It doesn't bark. It neighs. It's only got 1 toe, not 5. But all of the medicine and all of the biology was comparative. And what's fascinating about fish is that they share most of the common biology with us. Now, sending the right signals for us has turned into a Tinder app, seemingly. And And now seeing the right signals involves various ways of creating the right conditions for an event that allows babies to be made. So there might be roses, there might be wine, and look, love has sprung. Now, when you reach this point, there's an opportunity that sets before you that you're going to need access to habitat. So habitat becomes critical in the baby making if we're going to make babies. So we need a nice sort of setting, and it needs to be comfortable, the right conditions, preferably warm, maybe a bearskin rug, and voila, we have a child. But we must have hygiene, we must have food, we must have shelter if the progeny are going to survive or they're going to die. So keep this little pattern in mind. It's very familiar because we're very human. And fish are a bit remote because they're under the water, but it's incredibly the same. So when we talk about fish, I'm going to run you through a little bit of other biology information about how aquatic food webs work, about the water cycles, so about how water comes to be in a river and what it turns into or doesn't turn into, depending on how that river works. We're going to talk a little bit about land use and about the various things that then lead to pollution in water. So these are things that change the water from being quite a healthy place for aquatic food webs to work to being places where they start to break down. And we'll look at all these consequences from a fish viewpoint. So we're kind of be fish focused, but we're going to talk about all the bits that you need to get to the fish. Okay, so the food web starts, and this is my really basic, because I'm not very good at graphics and my son jokes about my computer skills. So the base of the food web is a big pyramid, and it's made of tiny microscopic organisms, bacteria, fungi, and viruses. They make the bottom of the food web. So they're the biggest numerically by far, and the biggest by biomass. So total tons, they're actually the biggest thing in the food web. So critically important. Now, sitting above them are what we call our primary producers. These are the plants, but they're not all big, lush, macro-sized plants. They include microalgae, so tiny microscopic things that if we get enough of them, the water will look green. But even in blue water, clear-looking blue water, there'll be algae. There'll be diatoms, different types of algae, but they'll be there. And they're capturing the sunlight from the sky, and this is what is powering the food web. It's the energy of the sun, the magic of photosynthesis. It makes carbohydrate, it makes sugars, it makes fats, and it makes proteins, all in those cells. So the first useful molecules to make an animal, they all start with your primary producers. So this plant life is critical. Without it, nothing happens. Now, above that, we've got our consumers, so things that are going to then eat the next stage. So everything eats everything. This is the nature of nature, is that everything continues consuming. There's a little bit of a loss on the way as we go up. So you get slightly reductions of energy transfer. Now, these are things that we call zooplankton. They're still microscopic, although some of them might just be big enough to see. If you're as young as me, you might have had a bag of sea monkeys as a child. Did you ever get given a little bag and you tear off the top and you pour them in and they hatch? You're like, wow, look at that. And then they molt. They're very exciting. They're like a kind of a stunt thing from the show. And so sea monkeys are a type of zooplankton. They're called an artemia, but they're one of these very early primary producers. And you can see inside this little guy over here, is the middle one the laser? Maybe? Top one. All right, there we go. Oh, hang on. Oh, hang on, went backwards. There we go. So those little cells inside, this is called a rotifer, they're algae. So he's been dining on algae, stuffed his face full, and is going to produce more rotifers to the tune of hundreds of thousands of them. Now, having hundreds of thousands of them turns out to be really important. So when we get to the next layer, we've got secondary consumers, so eating the next bit. And these are all these creatures, all sorts of worms, slightly bigger critters, more complicated critters. We've got crabs, we've got mussels in the sediment, we've got yabbies. And then here are our first stages of fish, our larval fish. So these are blown up in size. You're talking about something that's only a couple of millimeters long in life, but you can see big eyes, very tiny brain, a big mouth, It's all about eating. If you're going to be a baby fish and you want to make it, you've got to eat. So huge eyes, chase live food and grab it. Now, your chance of grabbing food changes with how much food there is to grab. Lots of food, easy to grab. Full belly, I'm going to survive. Not much food, a lot of effort chasing around. Now I'm getting exhausted. If I don't find food and I only have a couple of days to do it when I'm a baby larvae, game over. I check out. You never see me turn up as a trophy flathead in the fishery or a trophy anything. I turn into dust. So this is part of this stage of consuming this food up the food web as it goes, including platypus dine in this level, our galaxids dine in here. So these galaxids are fish that swim up and down our rivers. So we've got about 17 different species of fish in New South Wales that go all the way from the sea to the top of the catchment, if they can get there. Okay, and we'll get to some of the if they can get there problems. And we've got these guys in the food web dining as well. Now, right at the top, we finally make our way to the peak. We've got the apex predators. So the Murray cod inland, some of our apex predators on the coast. We've got trevally. But of course, we are the ultimate apex predator, not the cod, so we serve them up on a dish. They're quite nice. A little bit of a lemon sauce. And here we are, the ultimate predator, as we have been for a long time. Now, all of this flows back down again. Okay, so when a fish eats another fish, yes, the big fish survives, but it also makes waste. It's fish poo, feeds bacteria, goes to the bottom end, and the whole thing builds back again. All that nutrient is going round and round and round and round and round. So this cycling is critical. Now, water is cycling as well. So I pondered the question, where did water come from? And no one really knows is the answer, but it might have come from comets on space. It might have bubbled out of the mantle of the Earth at some point, in some process we don't understand. But what we do know is that there's been virtually no new water for 4.5 billion years. We have the same amount of water and it's going around and around. Now that has consequences because whatever water touches, it becomes. Right? So it doesn't stay itself. It's very good at adopting everything that it contacts and taking it with it as it goes. And so we see water changing as it moves down catchments. So in a perfectly functioning catchment like this, we have the water evaporating out of the ocean, evaporating from lakes, condensing in the sky, the wind pushing it onshore, it rising up when it hits a mountain range, cooling, falling as rain. We see it run off down the catchment, and these are our rivers, but it's importantly going in as well as off. The in and the off are really important because when it's not raining, our rivers keep flowing. And how do they do that? Well, that's because the in eventually comes back out again. Okay, so the percolated in water, the groundwater, eventually becomes surface water again. And whenever it's not raining, all the water in the river is groundwater feeding back into the river to keep it flowing. So this has real implications for what we've done to our water cycle, and we'll cover that. It moves around with gravity, with wind, and with currents. So it's highly mobile. It doesn't obey boundaries. So if we put a marine park boundary up, the water doesn't stop there and go, okay, that's a green zone, I'll stay on that side. That's a red zone. It doesn't listen to any of that. And we talked about that. Now, the other water cycle is called the small water cycle, which isn't really taught at school, but it probably should be, because it's an awfully big part of climate change. It's got nothing to do with CO2, though, nothing to do with burning fossil fuels. This is how we're driving localized climate change. What we've done is we've cleared vegetation off landscapes. When we take the plants off, we leave soil. Okay? Soil is brown, and brown attracts heat. Green reflects heat. So if you get your pizza gun, when you have a pizza and you point your pizza temperature gun at the oven, it says it's 380 degrees, time to shove the pizza in, but you point it at the bare earth in a paddock, it'll be 60 degrees C. If you point it at the grass next door, it'll be 25. There's over 35 degrees C difference. It leads to huge differences in evaporation out of the soil, and we dehydrate the landscape. But we heat the air up, because as soon as that ground is hot, the air above it is hot. And you know this yourself. If you walk out onto the hot bitumen road, it's black, it's hot. You walk onto the cool grass, it's cool. It changes the air temperature, and that actually completely changes rainfall patterns in the country. Totally changes the way that rain works. The other thing that water does, and that nature does, is it cleans the water as it goes. It uses plants and it uses sediment to clean the water. When we think of a river, mostly we just think, well, there's water flowing like down a tube. It's almost like it's a pipe going downhill. We think the water stays in the river, but that's not what the water's doing at all in a healthy river. It's actually going along, down, under, back up again, along, down, under, back up again. So the river's actually flowing under the riverbed as well as above the riverbed. And when it goes in, it takes with it its excess nutrient, and it can get trapped. The nutrient can get held underground instead of continuing to increase in the river and pushing too much nutrient into the river. So this is a critical process to keep rivers healthy, is having a working riverbed, a functioning riverbed. And there's bits of life that make that possible. And the bit of life that does it mostly are insects. So whilst mosquitoes are pesky and sandflies are dreadful, insects in general are completely essential. But we're also got problems with insects in that we're losing them dramatically. So colossal collapses in insect populations. We're down somewhere around 70% of the biomass of insects are gone. Now, insects do things to the bottom of that river. Their babies go down there and they burrow. They dig little holes, and that helps let water into that substrate. And they do really cool things. Some of them lay like a little tube of glue and they live in it. So they glue the sediment particles together. And so when it does rain, instead of the bottom of the river just washing away, it's glued together. The insects have literally built a scaffolding across the floor of the river to hold it together so it doesn't wash away. So it changes the water quality downstream. If they're there, the sediment doesn't move. It doesn't get turbid and cloudy. They're really critical. Now, I want to take it back a little bit in history as far as we can with the knowledge that we have. So I live up in Ballina, and this is the mob from Ballina in one of the earliest photos that I could find out of the Richmond Historical Society. Now, apart from the physique of these guys, which I'm envious of, the thing I want you to notice is the riverbank, which is heavily timbered with big timber, not little thin things, proper timber. And the river itself is full of big timber. This is what rivers look like. It's really hard to conceive of that right now because none of our rivers look like that. And there's a reason they don't. We changed it. We changed how rivers looked. Now, other parts of this same river, also the other important thing here is all these leaves, they're all insect habitat. If you want to understand how important insects are to fish, go to a tree, get a tarpaulin and wrap it around the tree, around the base of the tree, and shake the tree. And you won't believe how many insects land on your tarpaulin. All those insects are food. They fall in the water and the fish eat them. If you don't get any insects, it's a problem. The leaves themselves are food. The leaves are feeding that primary producer layer, building that food web. No leaves, less food, less primary producers. The pyramid shrinks. Okay, so the situation starts to change. Here's the lads up the top of the catchment now. You can see we've got beautiful sedges lining the river here. We've got melaleucas all along the side. So we've got full catchment coverage. If rain falls on that, that rain goes in, mostly, not off. The trees act like syringes. They inject that water into the ground. You know the water's clear because old mate here can see the fish. You can't throw a stick and get dinner if you can't see what you're aiming at. You also know there was an awful lot of fish there. It was so reliable. This was as reliable as going to Macca's to get dinner. You could literally walk to the river and get dinner with a stick. Give that a go when you get home on your river and see if you go hungry. It's changed radically. It's profound to appreciate how rich the fishery was. It's extraordinary. Now, it all changed in part because of one of the great egalitarian acts in the Australian Parliament. Governor Robinson in 1860 put the Lands Act out, and it said, we want you to be free settlers. We want you to take up land. You peg it out, you pay us a little bit of coin, and it's yours. It's freehold. You own it. But it's conditional. You must clear the land to within 95% of the boundary. All of the native veg must go off your land. That was in place until 1985. The aspiration was born of this idea that we would become a civilized agrarian society, a civilized farming society. This was the concept, and the idea was around building personal accumulation. It's a really interesting shift in values that happened from Indigenous values, where there was no such thing as personal accumulation. In fact, if you chose to personally accumulate in your mob, you'd cop a spear in the leg and be dumped off by yourself. There was no such thing. They have no idea what personal accumulation is. It changed. Now, the reason they wanted to become civilized is that cedar cutters were the first men out in the bush. They were convicts who'd escaped, and they liked several things, mostly booze and whorehouses were the things that were prominently written about. And they said that one of the surest modes of securing a friendship of a cedar cutter was to knock him down. He would return the favour, reduce your features to something unrecognisable, and then forever be your friend. This was the nature of men of the day. I hope that we may be friends, but with just keep my face in place. But this is what changed everything. When we started cutting logs, we had to get them out. We had to get them to a mill to cut them, to use them. So this here is what's called a desnagging barge. So all those logs that were in the river, we pulled out of the river manually with a block and tackle and with a steam-powered engine. We swung them with a jerry out onto the bank and burnt them. So all the snags in the Richmond River were pulled so we could run freighters all the way from Lismore to the coast. Had to get the wood out. It removed the blockages. Now, when you take wood out, that wood is slowing water down. So the water will flow faster without obstruction. That means we dehydrate the catchment faster. There's less water there for fish when it's not raining. The water level will go lower. This is problematic. You also see, if you look carefully in this photo, this is what the riverbank became. You can see it's starting to slump because we've lost the vegetation that was holding the bank together. It's gone. That river is already starting to go brown, and we're only in 1880. We'd had first settlers on this catchment for about 40 years by then. By 1906, we'd cleared 98% of the catchment. We were very good at clearing. Now, we did it everywhere. We cleared the entire Murray-Darling of snags. We pulled them all out to run paddle steamers to get wool out, get grain out as we developed agriculture out into the Western districts. We did it in the Snowy. We cleared the Snowy of snags. You can see here, see the chains on the tree running up to the block and tackle. Again, pulling timber out to make them passable for access for boating because we didn't have highways. We didn't have railway first. Boats were everything, and so rivers were made passable to allow traffic. But we completely stuffed the hydrology and accelerated water off our catchments, and then started whinging about droughts that we made. We worsened our own droughts dramatically by how we've changed the catchment. The good news is it's fixable. It's completely reversible. And this is the positive news story out of this stuff. Now, we didn't just stick to the riverbeds. Of course, we cleared the landscape elsewhere, and we adopted a scale of farming, of broadacre farming in many of our Western districts for cropping. This is a good site where it'll be 60C there and 25 there. Okay, so big difference in temperature. big difference in holding the soil together. We put rainfall on this, we make a mud milkshake. We put rainfall on this, we hold the roots are holding the soil together. So the roots make sugars and they're sticky and they hold the particles of soil together. So you don't lose nearly the soil off this landscape if it remains vegetated. We also did this. We decided in the 50s to adopt chemical farming as our mode of agriculture. And this changed the biology of the soil, completely changed the things that lived in the soil, because not only did we kill weeds, but we killed inadvertently other things, bacteria, fungi, earthworms. These died in the soil and our soils actually collapsed. Many of our rural soils have compacted down between 10 and 20 centimetres of drop in elevation because all the things that were living in there aren't living in there. So they drop and they compress. Now, if you pack down soil and then rain on it, the water doesn't want to go in. It wants to go off. And what you'll notice is our floods are getting worse. Our flood peaks are going up because more goes off than goes in. And it's getting worse because this hasn't stopped. We haven't let off. We're keeping on going with how we're doing things. So what we see is decreased infiltration, more runoff, more sediment. And with our mode of farming, fertilizers and pesticides move with the sediment and water and they end up in our waterways. It's not where we want to put them, but that's where they end up. You can see we've disrupted this small water cycle. So now we've gone from nice, cool 22 degree, 25 degree cover to 50, 60 degrees. We've got heat now blocking cold air coming in. You just can't get the moist air in. You know that water, when it evaporates, is cooling, right? So you stand under a sprinkler, you get cold, right? This is what we've lost. It's part of why things are heating up is because of how we've changed the landscape. This is what happens in consequence to the sediment. This is where it ends up, is we take our sovereign resource of topsoil, which is very shallow and thin and very valuable, and we push it out to sea and we cover up the nearest snapper reef and we stop it making snapper forevermore. This is the Richmond River. This isn't actually a big rainfall event. This is only about 50 mil. Right? We get heaps bigger rainfall events in Ballina as you do down this way. 50 mil is not a big rainfall event down here either. This is the consequence off the catchment. It's hundreds of thousands of tons of topsoil movement off the catchment. It's colossal loss of soil. We know where it's coming from. Most of it is actually from the banks of the river collapsing in by volume and then to the country which is not vegetated. So that's where we know where that's coming from. Now, back to our food web. If the primary producers are plants, they need light. They need sunlight to make themselves go. They need the energy of the sun. If you've got mud, no sun. No sun, no fun. The plankton collapse. This river, when they first sailed in here, was covered in two things, oyster reef and seagrass meadows. There were dugongs reported feeding in the Richmond River. Ain't no dugongs in the Richmond River no more. Ain't no seagrass in the Richmond River no more. It's all gone. No light, no seagrass. No seagrass, no primary productivity. We haven't taken the energy up to the next level. The energy stopped moving. Not surprising, it's really hard to catch fish now. This river used to have over 60 commercial fishers. It has 3 left and they're all part-time. It's a massive decline in fish catch. We've lost food out of the food web. It's a real loss of tucker. If you don't eat, you don't shit, you don't shit, you die. This is the story of what happens in water when we get the water wrong. That mud, it's fine sediment and it clogs up the riverbed. So that little cycle of going down, we've actually broken the river's own filter by clogging it up. We've smothered the habitat and these invertebrates, these little mollusks, little worms, we've nailed a lot of those with chemicals that run in and concentrate in sediments. It carries phosphorus, which is a nutrient source, and pesticides into the river. These are things that are associated with increasing the chance of a harmful algal bloom, a bit like the story that we're seeing in South Australia at the moment. Now, so they were the first dehydrating steps we took, but we were very keen on dehydrating, it seems, because the next step we took was drainage. So that's the pre-drainage river pattern of the Richmond River. By 1910, we'd done that on the floodplain. Every blue line is a drain. There's a table drain between 1 and 3 meters deep. We dropped the whole water table of 1,000 square kilometre floodplain. We exited all that water to the sea. Think about the cooling capacity. Have you ever had an evaporative cooler in your house and you put a jug of water in, use a little bit of water to cool the air? We took all that water and we sent it out to sea, and we wonder why it's getting hotter. It's a colossal amount of water moved off the landscape. It's no longer available to the freshwater food webs of the system. Now, there's other things that we did that we'll call them inadvertent consequences. People didn't realise if you stuck a floodgate on our acid sulfate soil wetlands. This is a floodgate here at Rocky Mouth Creek. This is when it's discharging after high rainfall. This is completely deoxygenated water from rotting vegetation. So when you drain the landscape, the plants that want to live there change. So wetland plants, like the name, like being wet. They don't mind having wet feet. Sedges can have wet roots and they'll stay alive. But if you put paspalum and cover it with water, it'll die. When you drop the water table, all the plants change. You go from wetland plants to dryland plants, but then it rains north coast style and they go underwater and they all die and they rot, and then you have no oxygen. And because you've got a drain, you take all that rotten water and in 4 days you put it in the main stem of the river. Back when the mob were running around the landscape, it took over 100 days for that water to leave the wetland. It would stay there, it would bubble away, go through its process of decomposition in the wetland, and then slowly leach back into the main stem of the river without nuking it with this bomb of organic matter that comes out with our floods and drainage. So it's completely changed what's happened. When you drain acid sulfate soil, it makes acid. The soil's oxidized, it lets air in the soil, and it makes acid. And now this water here, that's just above lemon juice in acidity. If you want to polish your silverware, just duck down to Rocky Mouth Creek or Tuckian Barrage, put your silverware in, it'll go shiny. The acid will peel off the outer layer and make your jewelry go shiny. It's really bad for aquatic food webs. It mobilizes metals and it makes them toxic. Now, fish can't get through the gates when they shut. So when it's not raining, the gates shut. Fish lose access to the habitat. Those habitats make most of the prawns on the coast. So the salt marsh in wetlands makes most of the baby prawn food. Somewhere above 80% of the food comes out of those wetlands. No wetland access, no prawn food, way less prawns. Ballina used to have about 30-something trawlers working out of the harbour. We've got 3 left, and they catch about 50 kilos a night. It's barely worth turning on for the diesel. Fisheries collapsed. Down the Hunter in Hexham, we pulled the gates out, let the salt water back in, raised the water table. The prawn catch in the Newcastle fleet went up 200 tonnes a year. In 2 years, it took 2 years for the prawn catch to come back. Whoop, straight back up because we gave access, we got rid of the bad water, and the food web started working again. It made food. Bunta, back it came. It's reversible. But the Richmond, poor old Richmond, is not in a good way because we haven't reversed it. We just haven't fixed the problems. All right. I'll skip that one. So then we get to our freshwater dams, and you can see our rivers, we stuck dams in the way. So we thought it was a good idea to catch water. It was convenient. So we stuck dams in. Now dams, I mentioned those 17 fish that swim up and down rivers. Very hard to get past that. You need to really jump to get over that wall. It's problematic. But also how we manage them. So when the dam wall, it could be 30 meters deep there, and there could be 15 or 20 degrees C cooler at the bottom of that dam. Really, really cold water. So you can see here that the water out the bottom is more than 10 degrees C lower running out the bottom than normal summer temperature would be. Now, if you think back to my first little picture about the conditions you need to breed, you've got to be cozy. You've got to get the right temperature. Otherwise, for fish, the love light just never comes on. So we know about this. We've studied Murray cod. If we don't get the trigger for the temperature rising up past 15 degrees, the fish never think about spawning. It just never enters their mind. And so you get no babies, no lovemaking, no babies. Now, the distance, so these cold water persist for several hundred kilometres downstream. It actually takes a long time for the water to heat back up. So this is problematic in how we manage our dams. And again, it's things that we can fix. Interestingly, carp are a cold water fish. They don't mind it actually at all. In fact, they quite like cold water and they spawn readily in it. So when everyone says, oh, the carp have taken over the Murray-Darling, no, we opened the Murray-Darling for the carp. We set up the conditions. We made the bed. We handed out roses. We did everything for the carp to make it nice for them, but our native fish just don't like it. They don't like cold water like that. Then we took away the water, so we stuck bores in as well. So as if we hadn't done a thorough enough job by devegetating, so slowing rainfall, increasing runoff, putting drainage in, then we stuck bores in everywhere. These are the bores on the north coast. This is the number of licensed bores. It blew my mind actually. Every dot's another bore. There's a lot of holes in the ground when you start looking, and a huge amount of groundwater is pumped out. That water now is not available to go back into the river. Right, so we've taken away stream flow persistence. Now we know from broadly up in Northern Australia where we haven't messed with the rivers so much just yet, the bigger the wet season, the bigger the runoff, the bigger the prawn catch, the bigger the barramundi season. Stream flow persistence marries to production. More persistence, more production. Less persistence, less production. So what we see are the consequences of losing this stream flow persistence, okay? So if you have less water, so if you only fill your kettle up this much, it only takes 30 seconds to boil your cup of tea. If you fill it to the top, it takes 5 minutes. The same in the river. A little bit of water, it heats up. So now our water in our rivers, because there's no stream flow persistence, we don't have much in them. They get hot and they get cold and they get hot again. Fish hate that. Fish like, pretty steady, up and down fast, bad. They don't like it. They don't want to breed in it, and half the time they don't even want to stay alive in it. We get these nutrient consequences. This is harmful algal blooms. So this is cyanobacterial blue-green algal blooms. Now the fish mostly don't die of blue-green algae, mostly. They stay alive, swim through it. It's bad for us. It's probably contributing to our Parkinson's disease around these rivers. If you live next to a blue-green algae contaminated waterway, your risk of Parkinson's goes up. It's bad if you're trying to get water for your cattle. So blue-green algae will kill your cows. So that's bad. It's bad if you want town supply. So even if you filter that out, the water's going to taste like rubbish and everyone's going to complain, and you're going to have really expensive town water because you need really expensive filtration to turn shit water into tasty water. And even then, it may not still be super safe. It's just better than it was. The key with water is don't let it get like that. So think about the things that make it go like that. And this is things like too much nutrient from our fertilizers primarily and our wastewater. This is what drives the blooms. It promotes harmful plants and weeds. So often we'll see our waterways getting covered in aquatic weeds. Those plants are there because the nutrient's there, not because they're a bad plant. They're there because there's so much nutrient that the plants that used to be there can't hack it. They don't like high nutrient. Most of Australian native plants do not like high nutrient. If you fertilize natives, they'll die. We've fertilized the river, we've killed our native plants, and we've promoted weeds. That's what happens. And it reduces oyster attachment downstream. The babies can't find a good place to live, and we create ammonia toxicity. Then if the algae get a few cloudy days, so they don't get fed by the sun, they can die. and get a big algal die-off, and that sucks the oxygen out of the water, and then the fish die. That's the time when the fish check out. So we lose them with an oxygen crash in the river at the end. But all the things that led to that, a lack of water, too hot, too much nutrient, pesticides harm the plant life. So many things contributed to get to here. So it's really important to try and understand them all. I know there's a lot to take on here, but you get to record it and you can watch it again. Pesticides are another thing that we've gotten hooked on, and we're increasing our use massively. So we've in the last 12 years, we've doubled the volume of use of pesticides in Australia. We're out over $4.5 billion worth of pesticide applied to the landscape. It's a lot. And it does what all things do. We use it all over the place. That doesn't stay looking like that without pesticide. It's very hard to make a golf course look like that. But if we go to the drainage point of the golf course and look at the water running off, and Kirsten gets her samplers in there and measures, we'll find all kinds of things that they sprayed running into your waterway. We put them on directly into macadamia orchards, and tiny little particles that drift in the wind end up in the water. When we spray an orchard, 40% of the spray hits the target, kills the bug. The rest goes on the dirt. Then it rains, off she goes. Or if it does go in, it goes and contaminates groundwater. So it never goes away, this stuff, unfortunately. And we tend to like products that have long action. So long acting, kills cockroaches for 3 months. Yahtzee, no roaches? What happens to the chemical? Kirsten finds it in her samplers. It persists, it doesn't break down, and it moves. So these chemicals, we often use them to target insects, and insects are so important to the river. They keep those sediments alive, they feed the fish, they're critical, but it's toxic to them. So we've got less sediments, less burrowing. The insects are what eat the leaves that fall in the river. They kind of munch through the leaf matter. It's important that they do, because they turn that into a yabby or into an insect. Like take the energy of the leaf, turn it into themselves. If you leave it there, bacteria break it down and they start to consume the oxygen. So you hear about black water kills. You would have heard that term maybe of, the black water killed the fish. Well, bits of the food web were missing to assimilate that. The frequency of black water events is going up and up and up and up and up. Everyone's like, oh, they're just normal. It's what happens when it rains. Well, if it is, why didn't it used to happen? We've changed things that are making it happen, fundamentally changed things. We put fungicide everywhere. Victorian EPA did a study on fungicides and found it in 95% of their samples in a flood. So all the flood water that went everywhere had fungicide in it. So we fungicided the whole landscape and then wondered why the fungi weren't doing their job when we used a targeted chemical directly against fungi to kill them. They cycle that nutrient. No fungi to cycle it, bacteria get involved, oxygen issues, more issues. We lose that zooplankton food, so that next layer up, the bit that the fish want to eat, that you need plenty of it for them to eat, collapses down. We lose the densities and we have less fish survival and we get more algal blooms. These are the consequences, and our native plants disappear. We've got our urban area, which we've changed dramatically as well. So we move off farming. We've certainly changed our urban water cycles as well. We've got things that we flush down the toilet. So before 1950, it was mostly just poo. It was mostly nitrogen, phosphorus, and a bit of organic matter. Now it's, I've got a headache, it's ibuprofen. I've got a cancer, it's chemo. Straight in, straight out. In fact, it's whatever you put in your body is going out. And it's going to the wastewater treatment plant, where I think mostly we just go like this. We go, well, they're treating it, right? They would catch it, right? They would get it all out, right? Isn't that what that does? So being a nerd scientist, I look at, well, do we? Is that what happens? And the answer is kinda. We catch some of it. We catch the chunks. We definitely don't let floaties pass for the most part. So Bondi cigars aren't a thing anymore. Right, so we stop that, trap the big heavy stuff. We lower some of the chemistry, but about half of our wastewater plants are still emitting glyphosate, Roundup, out of the effluent stream of the plant, because 80% of them had Roundup coming in. So we dropped it by 30, but it's still going out. Ibuprofen goes out. We can find all manner of chemistry running out of the plants. So they're just imperfect. And we use the engineer's motto, which is the solution to pollution is dilution. And then we do this one, and we'll hope she's all going to be right. She'll be right, it's Australia. Except we've run out of diluent. Remember, there's no new water. We just ran out of diluent. It was working pretty good to start off with. We were literally letting it out and it was fine. There was no drama. But the load, we're now up at what, 28 million people in Australia? That's a lot more bums. That's a lot more chemistry. And it's all going to the same water. No new water, same water. So what we see is all these chemicals that you might hear about on the news, hear about the PFAS from the firefighting foam and the airports, but also coming out of car tires. So runoff from roads always contains PFAS chemicals. It's coming out of your fry pan. So every wastewater treatment plant is actually a PFAS hotspot in the country. They aggregate it. They catch most of the PFAS, about 90% in the sludge pond. So the sludge builds up. Okay, great, they've trapped it. Where does it go then? Well, we can't have the sludge pond overflowing because that will cause a bad odor and everyone in town will complain. So we desludge the pond. What do we do with the sludge? Well, we don't know. It's expensive. It's contaminated waste. So we go, well, it's got some phosphorus in it. It could be useful for agriculture. So we truck it and we spread it back onto the landscape. 75% of our biosolids, we call them, sounds better than toxic waste. We spread them onto agricultural land where we grow our food. It then rains and it moves back into our water cycle. This is what we do in our infinite wisdom. So our pharmaceuticals end up in there, our personal care products. So any what do they call them? Products that have things to scrub your skin, micro beads, just to make your skin feel puffy or something. I don't know what it does. Doesn't seem like a great idea. Or if you need to go to Mardi Gras and put sparkles on, it's all plastic. It all washes off. It all goes into the waterway. Plastics are a huge issue, massive issue. We had a survey, EPA did one. Every single estuary in New South Wales is contaminated with microplastics. We catch a lot of them in the wastewater plant, but they all run out too. Every time you wash synthetic clothing, those plastic fibers break off and they go to the wastewater plant. Now, most clothing, unfortunately, is plastic. So most is nylon, polyester, or pseudoplastics, rayon, a few others, but it's mostly plastic. And then we find pesticides in there because we use heaps of them in our home and we can buy them, or you can buy this in Bunnings. Ant sand. I hate ants. So you buy ant sand, pour it around your house, it runs into your storm water, which connects with your sewer pipes often, and we end up with it running into the river. These are really persistent chemicals. This one here is a PFAS pesticide called bifenthrin. So it hangs around a long time. It's great, kills ants for a long time. Also kills fish for a long time when it ends up in a river, or kills invertebrates anyway in the river, which then kills the fish. So these are the problems we have. Now, the consequences can be really subtle. So I mentioned you've got to get the hormones right. You've got to get the mood right. The hormones have to be the right time. You can't make love on any day of the month and have a baby. The hormones have to be right. The woman has to be ovulating. The man has to be not comatose if it's going to work. The hormones in fish are able to be disrupted by a lot of this chemistry in their environment. We call it endocrine disruption. It's another word for hormone disruption. So these are things like your testosterone, your estrogen, that make you more female or make you more male, although we both actually have both of those hormones in our body. But it's what's changing. This is a fish that's growing eggs in its testicles. Now, for the men in the audience, it's worth bearing in mind what that would feel like to have a couple of double yolkers sitting in your testicles. This is happening in fish. So where Ben is at Bribie Island, when Cyclone Yasi tore down the coast, lots of runoff, lots of pollution. There happened to be a run of cobia in the hatchery at Bribie Island. 17% of the cobia grew both sets of genitalia. We made hermaphrodite fish or intersex fish. That's not normal for cobia. They're boys and they're girls.
And that comes from the surf side.
That's the ocean side. So is it happening? Yeah, 100% it's happening. We watched it, we measured it, it's happening. It's happening to us as well, but that's another story. But it's also causing immune suppression, and absolutely his sperm count's down 60%, 2% a year declining sperm count. Toxicity of insects, harmful algal blooms tie in to the way the chemistry is affecting how these organisms work. It's really not good. So what to do? This is all pretty heavy stuff, isn't it? It's like being in a dark, black place. Like I got asked once, do you get invited to dinner parties? I said, yeah, not much. But knowledge is power, right? So if you can understand the things that are contributing and realize that you can't just say it's just, it must be the weather anymore. It's not it. I think we're missing it. Then we can do something else. Now, Drucker was a great man. He said, you can't manage it if you don't measure it. All right, so how are we going to convince anybody that something has to change? And this is where citizen science water quality comes in, I think. This is the proposition. This is the sales pitch, really. and this is really what we'd like feedback on, to be frank, as to whether you think there's any legs, whether you think you would participate. The idea is it will help us identify where, what, and when problems are occurring in waterways. So by monitoring certain parameters in water, some of them can be very easy. They can be like measuring sediment in a turbidity tube. So how cloudy is the water? Some of them may be able to be measured by our phones in terms of what color is the water. So it can be very quick activity, take less than 5 minutes of your time. We think we can build interfaces that take that data. So here we are down at the river measuring water. This is down at Port Stephens, measuring the pH of the water with a little test kit. We can use that to educate our communities about the water. So the stories I've told you, you can tell other people. It's the critical bit, really. I can only talk so much to so many people, but if one more person talks to one more person, then well, that's double. That's great. We're getting somewhere. We want to create visualization of the data so people can see it, because it's sort of a weird thing, water quality, to talk about. It's like, what is it? So we think mapping tools will be the way to go, so that we have you collecting information, the information going up to a cloud-based server, holding the data. Someone can jump onto a map and go, what's in my water? And they go, oh, look, there's been 8 water quality measurements in the last month. Click on the dot and show the graph of what's happened in their water. It's gone up, it's gone down. And they might go, gee, I saw a fish kill last week. That's funny because that immediately before that, the water went bad. Right, okay, what happened there? You can start to do cool things like blitzes, where you get a bunch of people in a group and say, okay, today we're going to go 5 kilometers up the river each. And at midday, everyone sample. So you get this snapshot of what does the river look like at all these points on one day. And so if there's a point down the river where suddenly the water goes from being pretty good to pretty bad, you're like, okay, little circle around there. There's something happening there that's changing that water. What is it? What land use is it? Is it mining? Is it stormwater? Is it wastewater? Something's changing there. And it helps us direct effort and say, right, let's go and look at what's there. Let's go and talk about what's there. And let's see if we can mobilize resources to fix these things. So there are some resources. We've got Landcare doing things. We've got Ozfish doing things. But we need to mobilize much more resources if we're going to correct some of these things that we've bent off into the wrong direction. So that's the proposition I'd like you to think about. And Kirsten's going to talk about some examples where she's created that in micro. But we kind of want to turn this into a bigger scale of event. That's the aim. All right. I think that's the end of me. Oh, these are just other things that we can do. Yeah. So change the way we do food and fiber. It's a big transition. It has to be a funded transition because you've got to bring farmers with you. You can't have no farmers. Got to have farmers, but we've got to have farmers doing food and fiber differently. We can't do food and fiber like we are now and have good water quality. The two, they're just going off like that. So we've got to bring them together. You can plant trees. That's my boy. We're out planting trees on the riverbank. That's with Ozfish. We can stick snags back in the river. So Ozfish is getting involved in that, and some other groups too. We're actually putting habitat back in rivers. Of course, that you've got to wonder where the stump came from. It was probably a highway bypass, but at least we managed to get it back into the river. And we can slow the flow on our landscapes with contour ploughing. So there's groups working with those sort of strategies and training people. That one there's from Tarwin Park Training. You might have heard of a guy called Peter Andrews. He had a couple of Australian stories about slowing the water down on the landscape. So the idea is you hold it up the hill, give it more time to go in, less time to race off. So he's a big head of ideas, and they're sensible. They make a lot of sense for water on our catchments. The Malone Institute are also working in that space. So there's some good things getting going. All right, I'll shut up now.
Okay, so what do we know and what do we need to know? I'm going to try and do this as quickly as possible in the interests of time. But first of all, I just want to acknowledge that we're on Gumbaynggirr country. Gadigal, the sea, is actually the totem of the local Gumbaynggirr people. And they well know that Darang Nagalu, Darang Yama, good water, good fish. So, yeah, really respect the traditional elders and their management of sea country. I just want to start actually by talking about planetary boundaries. So this is a graphic that comes from the Stockholm Resilience Institute. And ultimately what they're showing here is that the Earth has boundaries beyond which it actually starts to tip out of balance, and we start to push beyond the capacity of the Earth to actually, sustainably support biodiversity and humans. So what you can see here is we're expanded out into the red zone in quite a few of these areas, which are a little bit scary. Over here on the right, we've got genetic and functional diversity or integrity. And this does actually include our fish stocks in terms of overfishing. And as Matt was saying, our aquatic food webs. So we have to support all of those organisms that support the fish. We can also see down the bottom here that nutrient pollution, again, something that Matt was just talking about. In particular, phosphorus and nitrogen, they belong on the land. They do a lot of good jobs when they're there being used in agriculture, but they are getting out into our waterways from both agriculture and urban wastewater. And then up the top here, I'm really highlighting the novel entities, which is referring to synthetic chemicals. So this includes our plastics, our pesticides, our pharmaceuticals, endocrine disruptors, PFAS, all of that sort of stuff. And all of those things are actually worse than climate change. And there's been so much effort in terms of climate change. The climate is changing. It does change. We have to adapt to that. But all of this contributes to that problem. So if we can actually solve some of these problems, we can probably also help reduce the speed of climate change. Coming back, I guess, onto a local level now, I'm going to talk to you about New South Wales and what we actually know here in terms of water quality. So the main water quality information comes through the Department for Climate Change, Energy and Water, and basically they've got this thing called the River Condition Index. And this was published in 2023. And I guess the good thing about it is that it recognises that there's a bunch of things that do actually contribute to the condition of rivers. Overarching is the catchment disturbance, so the amount of land clearing. And clearly this is going to influence the hydraulic stress. So this is really related to the amount of water extraction for agriculture and other such things. Geomorphic condition, this is looking at the connection between the main river flow and the good healthy floodplain floodplains and groundwater. So again, all of that stuff that Matt was talking about. Riparian vegetation, keeping that vegetation on the banks and preventing a lot of that sedimentation. All of these things affect water quality and ultimately biodiversity. So there's a link between these things. So the department does come up with a little bit of an index for each of these things, and they've mapped them on a sub-catchment scale for New South Wales, and then they put all of these things together into one big index. I'm going to talk in a little bit more detail about water quality, the biodiversity and the catchment, because those things are actually quantifiable. A lot of these other things are just based on modelling and predictions. So this is basically what it looks like. So this is what it's put together into that one water quality index. So catchment disturbance, basically the data that they've got for this is based on land use from 2017. So yeah, just a little bit out of date, like nearly 10 years now. And they also get infrastructure data. The land use is based on a weighting. So things like horticulture, irrigated crops are basically the worst rating. Whereas wilderness, national parks, that's the low level of rating. In terms of the index, they also feed in infrastructure. So looking at roads, this is data from 2022, so a little bit more recent, but of course it's not going to consider that sort of major highway bypass that is actually contributing to significant water quality issues in our local area that is not being monitored by anybody at the moment, and surprisingly lack of siltation catchments and whatever else, but different story there. They also look at land cover change, and that data comes from 2017 to 2019. So yeah, basically what that comes back with is a map like this that's saying, oh, our catchment disturbance is not that bad. I mean, I just find this map astounding. I don't know if any of you are a little bit surprised by that, but yeah, I would have thought that there was a little bit more poor condition in more areas. But it is partly due to the historical use of data, as well as the fact that it's done on an average for a sub-catchment. So we're not looking at individual spots, we're looking at big areas and then actually averaging them. So the fish community, so the biodiversity data, originally this was supposed to be macroinvertebrates, all the things that feed the fish and the fish, but they didn't have enough data on the invertebrates, so they've just gone back to fish data. This is based on a data set that was published in 2016, but it's actually drawing on data from 2009 to 2012. So again, quite a bit out of date. There's a lag time, but they do include the expectedness. So what type of fish would you expect in these rivers? What level is native fish as opposed to introduced fish? And what is the recruitment potential? Are they actually breeding in these river systems? So all of that is put together, and it comes back as actually pretty bad for some areas and not so bad for other areas. So it's definitely discriminating. And I've certainly seen that in some of the eDNA biodiversity data as well. And then water quality. So with respect to water quality, what they're measuring here are nutrients, nitrogen and phosphorus, turbidity. So this is actually how clear the water is, whether it's got sediment and algae and other things in it. Can you see through the water or not? Dissolved oxygen, the pH and electrical conductivity. So that's really looking at salinity. And clearly that's relevant in freshwater habitats. It's using a 5-year data set because water quality is really variable over time. So they've got a little bit more data, and they're using that data between 2016 to 2022. And basically it's looking like this. I was kind of surprised to see that there weren't really any regions that were regarded as in very poor condition. And this is probably due to the fact that all of this sampling was done before the floods. And I think some of these would come back as worst water quality now. So basically putting all those things together, they come back with the condition index, and just showing you, this is our local area. We can see Coffs Harbour here. We've got a bit of a bad area here, which is Bonville Creek. And then up around the Clarence River, a couple of bad spots, and down around Nambucca. If we have a look at the catchment disturbance, it doesn't look so bad. And yet when you drive north of Coffs Harbour and you look at the escarpment and you see, all of those steep hills that have been converted to nets and hothouses, I think there's probably a little bit more disturbance there than is indicated. This is the fish. Most of our region is kind of in that moderate condition. And then the water quality down here, a few little patches in some areas again. Whoops. which are regarded as a poor condition, but mostly we're in that sort of moderate condition. So that's what we're looking like in this particular area. Now, some of the limitations with this water quality data set from the River Condition Index is that there are some spots that they don't have data, so these grey bits are generally missing. There's a lack of spatial coverage in the sense that they're looking at whole subcatchment areas and just averaging that, so you're not getting the fine scale data. Temporal coverage, I already mentioned, I guess there's that lag period between the time the data is collected and when it's actually available to be used in an index like this. And generally we're dealing with data that's about 10 years old. It excludes the more recent extreme weather events, including floods, droughts and fires. And in terms of the biodiversity input, it's only looking at fish, not all of those other organisms. And the water quality, it misses all of those toxins, the metals, the pesticides, etc. These are not being monitored by the New South Wales government at all. And the most bizarre thing that I was kind of surprised is that they admitted that there's no field assessment or validation of the model's outcome. So they've developed this model, but they haven't actually then gone back into these subcatchments and checked that those catchment clearance rates or whatever else are correct. They do say in the document that changes are made to the data if local knowledge indicates that this is required. And I see that as a little bit of a positive in the sense that it suggests that if we collect the data, we can actually give it to them and maybe they'll update their map. Don't know if they really will. It depends on whether they trust how we've collected the data, but hopefully if it's done rigorously, they actually will. So what are the opportunities here? eDNA is something that we've been doing as a project in collaboration with the New South Wales Department of Primary Industries and Regional Development, and we've just been focusing on the estuaries. So we've actually sampled 33 estuaries along the coast, and we've got sort of 9 central estuaries that we've been sampling more frequently. And this method is a way of actually just taking a water sample. So you can use these little syringes to collect your water. They filter out the DNA from the water. And DNA is just in the water from any organism that's in there, not just the fish. It can come from scales, bits of mucus, from the urine or the feces, feathers, all sorts of things, drop DNA into the water. So it's always shed in the water. So we filter these samples and then we send them off for analysis. You can just see here, we use the Wilder Lab, but there are actually other providers as well. This is just the one that I'm using and I've got access to. It's a little pack that comes. It's got its gloves, it's got its filters and little, some reagents that you put in after you've filtered them. And basically you just filter that water and then you send it back off to the lab and you can get all sorts of wonderful data back. This Wilder Lab does actually publicly release the data and you can actually choose for it not to be, but of course, generally it's good if it's publicly available. All of these samples here are largely the samples that we've done along the coast. But you can see there are other samples inland, and even some of these will be contributed by some other groups, maybe councils, but some are actually done by citizen science, because this is a technique that we can teach people pretty quickly and easily to do. So if we zoom in on just to some of the samples in this Coffs Harbour area, whoops, I was just going to show you. We've got some samples off the Solitary Islands here and then some in various estuaries. And I think I've just chosen one from Coffs Creek that I actually did with my undergraduate students. And when the data is available on their website, you can actually click in on any one of those little sites and anybody can go to this website and look at all of this data. And it will first of all give you featured species. So you can actually click on any of those photos and then it'll give you more information about what they are. But you can also go into the taxon results, which gives you a total species list, and then you can filter just for fish if you like. And doing this, I found that in the whole sample, we had 3,334 species. That's a really high biodiversity, actually, and 133 fish taxa. When I looked at some of those inland samples that have been done, we found 7 fish taxa or 4 fish taxa, most of which were introduced species. So, yeah, we're pretty lucky to have 133 species in our local estuary here. I was also going to point out with respect to this Wheel of Life, you can get it to generate this Wheel of Life. It may or may not mean things to you, but you can see a lot of the insects, the crabs, a good balance of diversity in insects. Our fish are down here. And, we've got quite a lot of fungi in this sample, and that's because it was collected after a rain event. So there was probably a bit of decomposing material in there. But the other thing that you can do is pick up introduced species in there. So we pick up feral species and weeds and other such things. So it's a good indicator overall of the health of the environment. All right, moving on to the other water quality data. So this is more government data. And I mentioned that we didn't have data in that New South Wales River Condition Index for the post-floods. But the EPA, in collaboration with DECUA, did actually collect some flood recovery data. Unfortunately, this project, it was running from 2022 until 2024 and 2025, and it then stopped. But they were actually collecting some really good data. But this data is available, a little bit of data from the North Coast, the Mid Coast and the Hawkesbury region. And there are also some real-time monitors out there. So basically, these are all the sites that they've been sampling. And what you can see here, they're looking at water clarity, so that turbidity again. They've got some information on algae, nitrogen, phosphorus, and bacteria. And you can look at the date period. There's not too many time points in there, but you can actually look over time, and you can choose any of those points there and get some more information. This is looking in our Coffs area. And what you can see, the most recent or the last one that they did was in January 24. And you can see certainly around Nambucca, this one here is phosphorus, and we've got nitrogen up the top. So around Nambucca, we've got a little bit of a nutrient problem there. We can see over here with respect to the, this is the turbidity. So again, we've got a bit of, turbidity problems in various spots. This here is bacteria. So this is E. coli or, fecal coliforms. This is indicating sewage contamination in quite a lot of our water, which is definitely concerning. And then over here, we've got algae. So that's an idea of the type of data that was available after the flood, but unfortunately didn't keep getting funded. These real-time loggers are actually still out there in the environment, and all of those that are in blue are actually, the data is accessible, but these ones down here, if you click on any of those orange points, it just sort of says, oh, you're not authorised to access this data, which is a bit of a problem. But this data looks like this, and this is just a point from the Clarence River. It gives you temperature, salinity, dissolved oxygen, pH and turbidity over time. So, it's continuously running, and that data is accessible. But the problem is that, there's just one monitor here, there and everywhere, and it's not necessarily representing the river. So this is where I wanted to show you that citizen scientists can actually help. This here is the Clarence River Guardian group, and basically they've been doing some great work, and this is their website. So what they've been doing is having a look in certain regions of the Clarence River, and they have also been monitoring dissolved oxygen, pH, temperature, salinity and turbidity, so those same parameters. And you can click on any one of these and you'll see how many samples they've done on a smaller spatial scale and over a more frequent time. So they're actually increasing the data collection both in time and space. And they focused on areas that they thought were problematic, as well as potential control sites up and down the river. And these problematic sites are areas where they've seen fish kills. So that was actually the trigger for doing this work. So any one of those sites, if they click in, I think this is this point down here, and this is a pretty bad condition for dissolved oxygen, and you can move through those different parameters. And they actually provide that as a bit of a video as well. But this project is in collaboration with Southern Cross University, and Professor Scott Johnson has been leading it. So he's converted some of that data, as you can see here. So upstream in the Coldstream Creek, through Shark Creek, South Arm, and into the main channel of the Clarence River, you can see these changes in the profile of here dissolved oxygen and here pH. And what you can see is in this area around Shark Creek, it's really dipping into this fatal area for fish. So as opposed to just having one point in the main river channel, the community has collected all of this data and actually shown where the problem's coming from. There's a problem around Shark Creek. It's related to acid sulfate soil, and it's actually causing low dissolved oxygen and low pH that is leading to fish kills. So yeah, this is the power of community data. In space and time, you can collect a lot more information. All right, moving on to sewage contamination. In terms of what's available on the web, there are 192 sewage outfalls around Australia, and you can see these on a database, this national outfall database. And it's really just showing you where they are. There's 121 ocean outfalls and 71 that are in estuaries and rivers. And generally, these outfalls are doing their job. There are quite a bunch around Sydney that are primary treated, which means they only remove the big, large lumps and everything else gets out. Others are actually tertiary or secondary treated. They're breaking down more of the material in there. But of course, this Malabar one in Sydney has caused a lot of problems because these poo balls were washing up on I call them poo balls. They can call them fatbergs, whatever they want. But essentially, they've been demonstrated to come from the sewage outfall. And they were going north up to the central coast and right down the south coast of Sydney. So these things can get out of a sewage outfall and travel up and down the coast. So what's the government doing to monitor sewage contamination in our rivers and estuaries? Not much. There is a Beach Watch program. So this Beach Watch program, it's actually an opt-in for councils, and the councils have to pay for it. So it's supported by the government, but the councils have to pay and they can choose not to. And the problem with this is that you can see this big area around Coffs Harbour to Port Macquarie. If you've got a lot of tourism in the area, the last thing that you want to do is advertise to the public that you've got problems with your water quality, because it's actually going to put people off. So councils like Coffs Harbour, of course, don't opt in on this unless the community actually indicates that there's a bit of a problem. So every so often they have monitored around Sawtell pools, but other than that, there's no data available. So again, for where there is information available, you can click in on these sites and you can get more information on what the current condition is and what it historically was like. If you want to sort of look where you might be safe to swim around Sydney, for example. I did a bit of sampling in this area up in the northern Coffs Harbour estuaries. So these Gumbaynggirr estuaries, that was actually a project with the Garby people up there. And we were looking at these stormwater outfalls. And I don't have time to show you all of the data, but just to show you one example from Corindi River, it wasn't the worst actually, Arrawarra and pipe clay. Here you can see pipe clay toilet paper coming out the stormwater drain. So clearly the council denied that there was a problem with this particular site. So, I keep taking photos of the toilet paper that's coming out that pipe. It's clearly got a problem. In any case, let's just take a look at Corindi. So here you can see 3 stormwater drains along the wall here. We sampled here and upstream and downstream. This first drain up here had really high E. coli just when it was sort of dry, and then after rain it dropped off at that site, whereas some of these other ones, they actually get higher levels of E. coli after the rain. When we have a look at this against the National Health and Medical Research Guidelines for what's safe for recreational use, that red line there is what's safe for primary contact, so surfing, swimming, etc. Anything above that line is dangerous for humans to swim or surf in. And then there's the line for secondary contact, and that includes boating and fishing and kayaking. Anything above that line essentially is not safe. And what I found in all of those estuaries that I monitored was that generally after rain, it's a problem. In Arrawarra Gully, I found that it's a problem all the time. So this is the limit for shell fishing. Tiny amounts of E. coli are safe for shell fishing. And the reason I point that out is because around these drains, you can see lots of oysters. And I don't know whether people are harvesting these oysters. This was after the Christmas or during that Christmas holiday period. I don't know if they were harvesting them to eat or to use as bait, but even handling oysters in these types of conditions is potentially risky. In terms of what we found in the oysters, for Corindi at the time we sampled, they weren't too bad, but Arrawarra Gully had really high levels of E. coli in the oysters there. And we also found in the brim, this is from swabs from the surface as well as the mussel. So you think, it's going to be okay if I cook them. But even handling them again can actually be quite unsafe if you're collecting them from a highly contaminated area. So those high levels on the brim, number 1 was a really big fish, and brim number 2 was a smaller fish and it wasn't as contaminated. So the longer they're living in these estuaries, potentially the worse they get. And of course, the risks are stomach infections, ear infections, eye infections. E. coli itself can cause stomach aches and diarrhea and other such things, but it's also an indicator of other pathogens. The government actually uses different pathogen, enterococci. E. coli doesn't survive well in salt water, so I probably underestimated the problem in my sampling. And let's just take a look at Arrawarra Headland, the beach. So here we sampled on an incoming tide, so all of that brown water, because I keep seeing people go out and surfing in these conditions. And we can see sampling here where it's coming out by the creek, but I also sampled up here where people launch their boats to go fishing. These are the safe limits. This boat launch area is actually really dangerous to walk through. So it's a problem, which I've told council repeatedly, but it seems to be linked to private sewage transfer stations on those holiday resort parks up there. And yeah, the problem is just not getting fixed nearly as quickly as I would like it to be. So what can the community do? This is a group in the Gold Coast, and they're part of the Surf Rider Foundation. They call themselves the Blue Water Task Force. And what they've actually done is set up themselves a mobile laboratory. This is their mobile laboratory. It does need a little bit of scientific expertise to do this, but they've got a really good protocol, and the community helps them collect the samples, and every so often they just do a blitz and collect a whole bunch of information. And what they found was that on some dates, there's a lot of problems. So these are rainy sort of dates. But then there's other sites which are red, that's bad, right across a bunch of different dates. And they identified these to the government, to the council. And ultimately, what they were successful in doing was getting the council to release some of their own data to the public, to more frequently sampling, and then investigating the source of the problem at these sites. And they now collaborate really effectively with council. So the community was actually really successful in getting the government to act on a problem that people kind of thought was a problem. They demonstrated it really was a problem, and then the government had to follow up because, you know, they were demonstrating risk to human health. Okay, back to the government again. So this is the microplastic survey that Matt mentioned before, and you can basically just see that they've graded the rivers based on the amount of, or the estuaries based on the amount of microplastics. And I just wanted to point out that Coffs Creek and Darkham get the worst possible ratings. So Coffs Creek, a lot of that is probably urban rubbish. Whereas Darkham, there's a lot of infrastructure for hothouses and netting and those sorts of things, which are probably contributing to that problem. So, yeah, I guess even our other estuaries, a lot of them are sort of only DLC, so there is microplastics everywhere. But, yeah, it's a little bit disappointing to get such bad ratings. So, yeah, that technical report is also available online if anybody wants to look further. Okay, so what is missing then from the New South Wales Water Quality Assessment? I've told you what the government knows with a little bit of extra. These are all the things, some of these Matt's already mentioned really, but we're looking at our pesticides, our pharmaceuticals. There's a lot of, you know, caffeine, cocaine, it pops up in wastewater really frequently. So a lot of these recreational drugs and yeah, basically a whole bunch of other chemicals that can end up potentially in our waterways. And there's very little assessment of them at all. So I started focusing in on the pesticides, a little bit more detail. And, you know, I think it's very important to realise that worldwide, this increase in pesticide use is about 160%. A number of countries, including the European Union and even recently China, have actually been making a strong effort to decrease their reliance on pesticides. Australia, 920% increase between 1990 and 2023. Like, that's not trivial. We've become pesticide junkies in this country, and a lot of these pesticides are banned in other countries. I think they're being offloaded into Australia because we're probably one of the few nations that still takes them. This is supported by our government generally because of poor regulation. And, you know, Australians are tough, but, you know, really, I don't think we're that tough. Like, it's definitely a big concern. All right, so what's happening in our estuaries? I need to first of all point out that there are probably about 8,000 different agricultural chemicals that are listed by the Australian Pesticide and Veterinary Medicine Authority. I can only screen whoops, I can only screen for 171 of these. So I'm screening for a small fraction of what is actually out there, and that's purely due to cost. Every single sample I'm doing costs me about $360 without preparation. So that's just, the analysis part. So when the government says that pesticide analysis is actually expensive, it is. And to do a more comprehensive panel where you might get to 500 pesticides, you'd be looking about $1,500 per sample. So it is expensive. And it's also hard to find because they come and go, and it's difficult. In any case, we have detected 55 different pesticides in our estuarine samples. The samples that I'm taking are not only water, but I'm also looking in sediment and estuarine biota. And actually, I find far less in the water than I do in the sediment or some of the other organisms here, including turtle livers. In terms of the pesticides I found, 78 have been banned overseas. We've got a mix of herbicides, insecticides and fungicides. 9 of these are not even registered for use in Australia, so they're essentially illegal pesticides. 51 of those 58 are regarded as highly toxic to aquatic life. That's how they're categorised, and that's why they're banned in a lot of other countries. And in terms of human health, 31 of these are regarded as serious human health hazards. So, these are nasty things that we're letting into our environment. In this diagram here, I'm just showing you all of the orange bars are pesticides we've found in oysters. And this is from the Richmond River, and the blue is what we've found in water. So you can see the oysters are actually picking up more than what's just in the water. There was only one that we found in the water that we didn't find in the oysters. 13 pesticides in total in this particular study, and in single oyster batches we found as many as 11 different pesticides. So yeah, quite a lot of pesticides in some of these oysters. And one of these was banned, and 4 of those in the water exceed environmental trigger values. But it's important to realise that we don't have sediment quality trigger values for pesticides, and we also don't have any sort of maximum residue limits in our seafood. And a lot of these other pesticides we don't have limits for either. And this is basically because the government is still assuming that they're not there and that they're not getting in and they're not causing a problem. But clearly they are. This study here was actually looking at a crab mortality event in the Clarence River, and we looked at different parts of the crab. And we also looked in the water. We only found 2. We found a bit more in the sediment, but we found all of these things in the crabs. So ultimately, in this particular crab kill event, we can't say for sure what was responsible for the crab kill, but we've done low dissolved oxygen and high turbidity flood plume experiments. Those things don't kill crabs on their own. These sorts of things probably do. So in total, we found 10 pesticides, 8 of which have been banned overseas, and 8 toxic metals. And there's sort of a bunch of insecticides in there. Propagite is a miticide, so that's something that is very likely to have a negative impact on crabs as well. This is some water studies that we did in Hearns Estuary. So this is a local estuary. And in this particular study, we found 9 pesticides in water samples. And you can see that gradient coming down into Hearns Estuary. Imidacloprid, some of the highest concentrations that have been found in aquatic ecosystems anywhere in the world. Yay, here in Hearns Estuary. And again, 8 of the 9 are banned for use in the European Union, and one of those is actually restricted for use. So, again, they're not nice things. Other countries know they're a problem to the environment. They're still allowed for use here. Now, this study was actually followed up by a local community group, the Sandy Beach Action Group. I think they call themselves Sandbags. And led by Maxine Rawling, they did repeat, a lot of that sampling that we did, but they did that using more event-based sampling, so looking after rain events. And they actually found 6 fungicides and 6 insecticides, so some of the ones that we'd found plus some more. So, the more you sample, typically the more you find. Interestingly, the EPA has more recently done some sampling in those same sort of estuaries. And so in the same estuaries, they only found 2 fungicides and 1 insecticide. And Willis Creek, that also feeds into Hearns Estuary, they found, one more a couple more insecticides, actually 3 insecticides and 2 fungicides. Now, you could think, oh, they're not doing a good job, but I've actually come back and recently sampled in Hearns Estuary as well, and I found similar to the EPA. So what's happened in between? Well, the EPA has actually started, or they started investigating between 21 and 23, 21 investigations, penalty notices, cautions, warnings, advisory letters, prevention notices and cleanup notices. Now, some of this actually required the farmers to instill catchments, catchment dams and things like that, and stop the water running off into the local creeks. So ultimately, this actually seems to have had some positive effect. And this was all driven by the community. The other thing that the council has been doing in collaboration with local land services is investigating some of these bioreactors. And this is particularly to do with runoff from some of these hothouses where you can kind of catch that water runoff. And they did this to trap nutrients and stop some of that nutrient runoff. So opportunistically, I came in there and decided to sample some pesticides. I found 11 pesticides below the hothouses, and as I sampled through that bioreactor, the number reduced to the point that there was only one downstream of the pesticide, of the bioreactor. So this is indicating that the bioreactor has actually been effective in removing some of those pesticides or stopping them getting into our waterways. Unfortunately, that bioreactor then blew out in the flood, but they are working on new models at the moment. So it's an ongoing research. But all of this was triggered by a community group. They noticed a problem. They sent out an SOS. They did some research themselves to create more evidence, and they put the pressure on the government to actually investigate and start doing things. Now, this community group will tell you that the problems aren't all over. It's actually a very complex problem and there's more work to be done, but it does show that community can actually have some effect when they work together. Of course, the Hearns catchment, which is here, is a big problem, and it's an example of multiple stresses. We have to look at the whole catchment to see what's going on here. We've got urban development up here, which is expanding, a wastewater treatment plant, some industrial development, and then we've got all of this land clearing that's going on because we're still converting from bananas to blueberries, and a lot of soil erosion. So what we're seeing is nutrient runoff, and that's associated with both the horticulture and the wastewater treatment plant, particularly with large rain runoff events. We're seeing biohazards potentially associated with the runoff from the wastewater treatment plant, but also because they're using that wastewater to irrigate horticulture. And one of the biggest problems is mercury. So mercury has actually been traced to, the source has been traced to the water that recycled wastewater that they're irrigating with from the wastewater plant. And that is getting down into Hearns Estuary. And you can see when we take sediment cores in the last 10 years, a big peak in mercury, and methylmercury in particular is very toxic. It absorbs up, bioaccumulates through the food chain into fish, into humans, not good. We see arsenic getting down into the lake. Again, in the last, there was a bigger boom about 50 odd years ago, one peak, and now another big peak in recent years. And I think this is because of the clearing. So that's arsenic was used as a fungicide in bananas. It's a legacy pesticide. It was also used in sheep dips and other things. But this clearing is now releasing that back into our catchment. And of course, the pesticides that I've just spoken about and other industrial chemistry, and all of this results in multiple stresses that ends up with an ecosystem which is basically devoid of life. The Garvey people tell me that was a really good place for catching prawns in the past. People still have memories of catching fish in this lake. But it's one of those clear examples of shifting baselines where, we think that this is normal now. A lot of people, a lot of younger people, 20-year-olds or something, they think brown water after rain is normal. That's not normal. When you're in a national park, you can see it's actually still quite running clear. But historically, it wasn't the case. And that is because of clearing of riparian vegetation and all of those things that Matt pointed out. But we can also see this problem with multiple stresses. And we also, I guess, really get that, I forgot my last point there, but this feeling for this whole interconnectedness between the land and the water, and that whatever we do on land can potentially affect what's happening in the water. I guess in terms of citizen science, we can't see things if we're not looking for them. A lot of this chemistry is actually invisible in the water, and the more people out there collecting data and contributing to both the spatial scale and the time scale of data collection builds up powerful data sets that we can then use to lobby governments and potentially to come up with solutions and monitor the effectiveness of those. Citizen scientists can help. Thanks. Don't know if we've got time for questions.
Sobering, shocking, potentially, a lot of what's been presented tonight. I guess we can't make any apologies for it because that's actually the reality that we're seeing. When you see the actual adult fish dying, it's pretty bad because you can be guaranteed all those other parts of the food chain lower down, which is supporting those fish, are also being terribly damaged or destroyed by it. But also, I think there's hope there because there's examples of communities being either developing the tools, or if we can get together and develop a tool to monitor water quality in a way that's useful. Not only are we raising awareness of the issue, you're quantitating it. There's I guess there's an aspect of keeping them honest in relation to talking to government or other authorities in an area, so that they can't tell porky pies about those maps that I saw where it said the catchments were in excellent condition when we know they're not, that type of thing. So I think from the point of view of our expert presentations, I hope you've all learned a lot. I mean, I was looking forward to seeing what they had provided there. So from now on, I think we could just open the floor to discuss local water quality issues. We do have a survey that we're encouraging people to fill out if you want to I guess, be part of ongoing future potential projects that'll come out of this scoping process. So tonight we just want to hear from you about local areas or local potential trouble spots where you might yourself or someone you know might be interested in undertaking some monitoring if we develop a water quality audit process. And then again, that particular spot, if it we need to actually devise ways to rank these different spots to identify the next step, which is to attempt some remediation and roll that out on a pilot scale, and then get the data from that to show improvement. That's our aim, is to demonstrate if you can fix these water quality problems, you'll be able to quantitate, the fish will come back. You'll be able to improve the environmental indicators that you're monitoring and use that to leverage off that information to roll it out more broadly to start fixing these problems. So that's what we're talking about, phases 2 or 3 of this project. But to get to there, we need to go to phase 1, which is to hear from you guys. Definitely fill that out if you're interested. Otherwise, just talk to us.
Survey takes about 3 minutes, and if you complete it, then run $100 easy at that.
Are we sure that'll make the difference?
It is. Let them roll.
But I think I'm particularly grateful to have both Matt and Kirsten on board here, because these guys, as you may have gathered during their presentations, these guys are experts, real experts in this area. And Kirsten has real data that you can, independent data that you can trust on actually the state of play. And we're really looking forward to working with her to devise these methodologies to get into this next phase where we have to price it up and sell it to the Rec Fishing Trust to say, this is a good idea. Mind you, like if they're after an answer to the question, where have all your fish gone? And it may not necessarily be, can anyone here see where overfishing may not necessarily be an accurate description of what's happened to these fisheries? What happens with food chains is food chains are never like this, with large numbers of fish at the top with nothing underneath them. If you shrink the bottom end of a food chain, what happens? the top end just has to shrink. There's no other way about it. So this is actually a far more plausible discussion about what's happened to the fisheries in these areas. And say, for example, for me, the light bulb moment is when we restore a tiny little patch of shellfish reef that has probably been gone for 100 years from my local estuary. And all of a sudden we've got 1,650% more fish in that area 18 months later produced, and it was demonstrated because they measured all the areas around, independently done by the local universities, who were great sort of have on board, not the government. But we demonstrated those fish didn't swim into the area, they were produced by the area. The other areas around still had the same number of fish, but this restored area had more than 10 times, 16 times more fish just by getting the habitat back. But we, as I said, I know in Moreton Bay, we still have a water quality that is acceptable a lot of the year. It's unlike East Coast of the US, where if you continue on this decline and let it go down and further, once you have the dead zones and the low oxygen zones like you see in these rivers, it doesn't matter what you do to your shellfish reef. There's no oxygen in the water. You lose them all. So we don't want to see them get that bad, but in some of the situations here in this part of the state, obviously you're down there as well.